Hi, welcome to educator.com. Today we're going to talk about correlation. All right, so first, let's go back and just briefly review summarizing scatter plots quantitatively and talk about all the other things we've talked about with scatter plots so far. Then we're going to talk about eyeballing the coefficient, the correlation coefficient, or what we call R, Pearson's R. Because actually, if you have a set of data that looks a particular way, often you could sort of ballpark where the correlation coefficient probably falls. And then we're going to talk about precisely calculating it. Then we're going to go back and talk about the relationship between R and B1, or slope, of our regression line. All right, so first let's talk about summarizing a scatter plot quantitatively. So shape we didn't deal with. We just looked at it and sort of said, maybe that's pretty good. And we'll talk more about shape in the next couple of lessons. But for now, we're going to leave shape alone in terms of quantitatively calculating it. But we did look at how to precisely calculate the trend, or by looking at the regression line, sort of that middle line in between all those lines that summarizes the middle of all those points. And that middle line really gives us the relationship between x and y, because it's a function that gives us, if we have x, we get y. If we have y, we could get x, right? So we could get the relationship between those two variables. And then finally, today we're going to talk about calculating strength. Not just looking at it and sort of saying, oh, it looks pretty strong, right? But instead, we're going to actually calculate the correlation coefficient, R. And really, that idea is simply how packed around the regression line is our data points, right? Are they tightly packed? Is it a strong correlation, like it's strongly packed around around that regression line? Or is it very loose? Is it very dispersed, where you can't really, it's not really sticking close to that line? Then we would have low strength or low correlation. All right, so first let's talk about just eyeballing it. Now, for a lot of data, you might have no relationship between two variables. And in that case, the spread should look something like this, where there's no real line in there. It's just sort of this fuzzy cloud of dots, right? And remember, each of these points are a case. And each of those cases have two variables. And one variable, x, is on the x-axis. And the other variable, we'll call it y, is represented on the y-axis. So that point represents x here and y here, right? Now, in this case, there's no relationship between x and y. Just because you know what x is, let's say we know x is here. Do we have any certainty as to where y might be? Well, not really. There's some y's down here, some y's up here, right? And even more so, what about if we thought x was here? Do we have any reason to say y is in a particular place? No, not really. And so because of that, a line won't help us here. A regression line doesn't actually summarize this very well. And it's because the correlation coefficient is very low. There's very low strength. There's very low adherence to the line. Now, moving out a little bit further, you see that this one is starting to have more of a sort of elongated shape, right? And this is still a fairly low correlation, but you could still see that there's starting to be a linear relationship between x and y. Namely, as x sort of goes up, y also goes up. So this is what we call a positive correlation. So there's a relationship between x and y that's linear and positive. Excuse me. Notice that right on the other side of this is the exact opposite, where it's the same shape, but it's been almost like flipped around, like as if we put a mirror here and looked at the mirror reflection, right? And in this case, it's the same shaped cloud, but now as x goes down, y goes up, right? So here we see the opposite relationship between x and y. And that's what we call a negative correlation. And because of that, the signs act accordingly. Here, the sign for this slope, for the slope that's negative, is negative 0.4. Here, for a slope that's positive, as x goes up, y goes up, as x goes down, y goes down, right? That's a positive number. And so we could easily, just by looking at the correlation coefficient, immediately know what kind of, roughly what kind of relationship x and y have, right? Now notice that as we go out even further, not only do the numbers get bigger, right, bigger out from 0, right, but the numbers correspond to how liney the data are, how much they correspond to a line, right? And so it's not really about having more dots or less dots, but it's really about how much do all those dots fit to a line, right? And that's why we often call it fitting the data to a regression line, right? Because we want to see, is it a good fit? Is it a bad fit, right? And correlation coefficient gives us the strength of that fit. Is it a really strong fit, or is it very weak and loose, right? And the actual maximum for a correlation coefficient is 1, and the minimum is -1. And that's as far as it will go. You can't have a correlation of like 1.1, right? And we'll talk a little bit about why. Now here, what you see is that this might have the same number of points as all of these, but it's just saying that there's very, very little variation from the line, right? So there's not a lot of variation out from the line. Whereas something like 0.8, you could see, it's better than 0.4, but it's not quite as liney as 1.0, right? And so that's one way you could just very quickly eyeball correlation coefficient. You could just look at a set of data, and as long as it's sort of elongated a little bit, maybe it's a 0.4, but if it looks, like a sort of tighter ellipse, maybe it's about a 0.8. And if it looks, very, very close to a line, perhaps it's close to 1. It's very rare that you get like 1, though. All right, in real data at least. But I want you to notice something. Correlation coefficient, other than caring about positive and negative slope, it doesn't otherwise care very much about slope. For instance, look at all of these situations. These are all lines, right? They're all very, very liney. They're maximally liney, right? Notice that these lines all have the positive slope, right? But they all have the correlation coefficient of 1, right? It doesn't matter whether as x changes, y changes very quickly, or as x changes, y changes very slowly, right? So the slope doesn't matter, except for just the positive or negative part, right? Same thing with the negative slopes. Even though the slopes are all different, they all have a correlation coefficient of 1, right? Now, there is an exception to this rule, and it's this line right here, the perfect horizontal line. Now let's think about what the equation for just a regular horizontal line is. In a regular horizontal line, it doesn't matter what x is, y is always the same. So let's say here, like something like y equals 3, right? So that would be like a horizontal line, or y equals -2, or y equals 0.1, right? So those are all examples of horizontal lines. Now, let's think about in the case of a horizontal line. It's sort of perfect prediction, right? Because no matter what your x is, right, you could tell me whatever x you want, I could exactly tell you the y, because y is always in this case 3, right? And so it's perfect prediction and it's perfect lininess, right? But the correlation coefficient is 0, right? And it's and we'll try to figure out why that is for horizontal lines as we figure out the the formula for correlation coefficient, and that hopefully that will become more clear. And I also want you to see there are many, many ways in which data can have seemingly no linear pattern or very weak linear pattern, because that's what the correlation coefficient tells us. So if we see, our data has a 0 as its correlation coefficient, do we know that it looks just like a cloud? No, in fact, it could look like any one of these crazy shapes down here. All of these distributions, all of these scatter plots have a very, very weak correlation. Because remember, correlation just means how liney is it. This one's not liney, this one's not liney, this one's not liney. None of these are very liney, right? Even though some of these have very, very regular shapes, right? Correlation coefficient can't tell you that this has an interesting shape. All it tells you is whether it coheres to that regression line or not, right? And so although these are very interesting sets of data, for instance here, there's sort of 4 rough clusters, right? And even though we could sort of see that when we just eyeball it, the correlation coefficient won't tell us that. Or in this case, this is sort of an odd data set, but even here, the correlation coefficient won't tell us that either. And so for all of these data, the correlation coefficient is very close to 0. So I want you to see, there's many ways in which you could have a correlation coefficient of 1 or -1, and there's many ways in which you could have a correlation, coefficient of 0, right? Just because we get the correlation coefficient doesn't mean we could see the shape of the distribution. That's why it's often useful to do a scatter plot anyway, just even for ourselves, just so that we know what our numbers are probably going to be describing. All right, so let's say we have this graph, and this shows us this nice correlation. It looks probably pretty high, like maybe something like R equals 0.8. So closer to 1 than to 0, but maybe not quite 1, right? So this is a pretty good correlation. And you might have 2 variables here, like for instance, perhaps this gives us the z-scores for some variable, like perhaps we're looking at twins and we want to know, does the intelligence of one twin, does the IQ of one twin help us predict the IQ of the other twin, right? So maybe it's true, maybe that does seem to be the case. So here we might put something like the intelligence of twin 1 on this axis, right? And then we'll put the intelligence of twin 2, their z-score from their IQ score. We'll put that on the y-axis, right? Now, when we have these scatter plots, it's very important that we don't lose sight of, that we could sort of toggle between the trees, the individual little dots, and the forest, the big overall pattern. When we look at correlation coefficient, we're sort of looking back, we're sort of getting a bird's eye view and looking very far away and sort of trying to see the overall pattern, right? And that's sort of the forest, right? But it's really important to remember, what are my trees? What are my cases, right? It's important to remember what this dot means. So that's what I mean by the trees. Like, you want to remember, what are your cases? What are your variables? That's always step 1 of looking at a scatter plot. And so in this case, it's not that each of these dots represents just one twin. It's that these dots represent a set of twins, a pair of twins, right? So here, this represents both twin 1, who's a little bit below average, and twin 2, who's actually a little bit above average, right? And so let's pick out another one. Let's say this one. This twin is a little bit above average. And guess what? So is their twin, right? So their twin is also a little bit above average. So each of these dots actually represents 2 people in this case, right? A set of twins. So you want to be able to switch your perspective and sort of zoom in and see the trees, but also zoom out and see the forest and try to estimate things like correlation coefficient, or even try to estimate, let's say, the regression line, to try and eyeball where that might be. Okay, now let's get to the business of calculating R. Really, you could think of the correlation coefficient as roughly the average product of the z-scores for x and y. Let's recap a little bit what the z-scores are. So z-scores are just giving you how many standard deviations away you are, right? Like, we don't want to know it in terms of the raw numbers. We want to know it in terms of standard deviation, right? So we don't want to know like how many feet away, but we want to know how many standard deviations away. So you could think of the standard deviations as jumps away from the mean, right? So how many of those jumps away are you? And that's the z-score. So here's how we calculate R, the average product of z-scores for x and y. So let's put the z-scores for x and y and multiply them together because we're getting the product, right? So the product is z of x times z of y. And I'm going to sum them together and then divide by n minus 1. Later on, we'll talk more about why n minus 1 is more frequent. But you could roughly see it's about roughly the average. And mostly it's because we're jumping from samples to populations. We need to make a little bit of correction. But this formula of adding something up and dividing by n is an average, right? And the thing that we're averaging are the product of the two z-scores. Now, for all of these formulas, you could think of these as like these little like z-scores as like almost like you could double click them, right? And if you double click them, sort of what's inside. Well, each z-score, let me write this in blue. So each z-score is really sort of the distance away from the mean, but not the raw distance. I want it in terms of standard deviation jumps away from the mean, right? So that would just be something like my y minus y bar, right? The mean, right? So that distance divided by the standard deviation. And here I'll just use little s, right? And also for z of x, that's just x minus x bar. So that's the raw distance away from the mean, but divided by its standard deviation. So I'll put a little x here to indicate the standard deviation of x's, and I'll put a little y there to indicate the standard deviation of the y's. And I'm going to multiply those together, and I'm going to add them up for every single data point that I have. So if it's my twin data, for every single set of twins that I have, right? And so, and then we want to divide all of that by n minus 1. And n is my number of cases. How many twins have you got, right? How many sets of twins have you got? Now, if we wanted to, although it goes without saying, this does implicitly have an I that goes from 1 all the way to n, because it's for every single one of my data points that I need to do this, right? Now, furthermore, we could sort of double click, right? Double click on each of these, on these little standard deviations. Now, how do we find standard deviation? Now, standard deviation is the square root of sort of the average distance away from the mean, right? So the average distance away. So square root of average squared distance, which just gives us average distance away, right? And so S sub y, right? This is, think about the distance, right? So we already know how to do distance because we've already done it, right? And it's average squared distance, right? Because remember, it's sum of squares over n minus 1. Now, remember, it's sum of squared distances because if we just add all the if we just got the sum of the differences, then we would just get something very close to 0, right? So we don't want that. And we divide by n minus 1 because that sum of squares is very small, so we need to correct for that by going from samples to population. So that's why we divide by n minus 1. And because we want the standard deviation and not the variance, we're going to square root this whole thing, right? Same thing for s sub x. It's the same thing except you substitute in x's here instead of y's. Oh, I forgot to put my little sigma notation because I want to do this for every single y. Right? So although it looks sort of complicated if we write the whole thing out, right? Like if we wrote the actual like unfurled or double-clicked version of the s sub y in there, it might look sort of crazy. What you do have to remember is ultimately this is the main idea you want to sort of like get out of today. And then you want to take a moment to think, okay, what's z-score, right? And then once you unpack z-score, then take a moment to think, okay, what's standard deviation, right? And hopefully you'll be able to unlock those things as you go. Then you don't have to remember all of that stuff at once. You could just remember them one at a time. All right. All right, now that you know the formula for correlation coefficient, now let's talk about the relationship between correlation and slope. Now, already we know that B1 and R have the same sign. So if B1 is negative, R will be negative. If B1 is positive, R will be positive, right? And vice versa, right? So we already know that they have the same sign. And because of that, they already slant in sort of the correct way, right? But remember, R doesn't have anything about rise and run in it. All it cares about is how much like a line it is, right? And so B1 and R have a very strict relationship, where R, when you multiply it by the standard proportion of standard deviation of y over the standard deviation of x, as long as you multiply R by this, and you could sort of almost see, you know, rise-ish over run-ish, right? Then you get the slope, right? And let's just do, let's just think about this in our head. So let's say R is 1, right? If R is 1, then whatever this proportion is, that will perfectly give us B1, right? Also, if R is 1 and these two have a very similar standard deviation, so the spread of y is very similar to the spread of x, then we should have perfect correlation of 1, right? So in that case, you would be able to sort of see like, oh, that makes sense. Like if y is sort of varying in a similar way as x, then yeah, they should have a correlation. They should have a slope of about 1. If y is changing more slowly than x, right? So so for every x, you only go a tiny bit of y, right? So in that case, this number would be smaller than this one, right? And then that would give us less rise, more run, right? So something that looks sort of less slanted, right? Something like this versus a slope of 1, right? So something a little more shallow, right? And that makes sense, you know, less rise, more run. On the other side, if for every y you go very, very little x, right? Then that would look something like this, more rise, less run, right? And so this gives us that perfect relationship between R and B1. All right, now using that information, let's try to solve this problem. Example 1. So here are, the 3 pizza companies that we've looked at before, Papa John's, Domino's, and let's say Pizza Hut. And it says, find the correlation between grams of fat and cost. And I think these, because I think these are for whole pizzas, and so let's make this $17.50. let's make this $18 and $20 because it's really cheap to have a $1.75 pizza. And it would be ridiculous to have 100 grams of fat in one slice of pizza. So, all right. So if you look at the examples provided in the download below, we could use this data in order to find a correlation coefficient. So in order to find correlation coefficient, I like to sort of break it down into the component pieces. And the big component pieces I'm going to need are the z-score for x and the z-score for y, right? And I'll say the z-score for fat and the z-score for cost. So z-score for fat and z-score for cost. In order to find the z-score, I would need to put in the difference between this and the average, right? One thing that might be easier is if we actually just create a column for averages, because we're probably going to need this again and again. So why don't we go ahead and get those averages? So I'm just getting the average cost as well as average grams of fat. And I'm just going to color it in a different color so that we know that this is an entirely different thing here. All right, now that we have that, now it'll be easier for us to find the z-score for fat. So here we want to get x, our fat, minus the average. And we probably want to lock that in place. Oops. And we want to divide that by standard deviation. And the nice thing about Excel is that it already has a function for standard deviation. And this one will give us the n-1 version, right? So I can just take this data, keep overshooting. And I want to lock that data down. I don't want that to move. Right? Actually, I probably want to copy it over to E later, so I'm just going to unlock the B part. As long as I stay in the same column, as long as I stay in column D, it'll use column B. But if I move over to column E, it should use column C, right? So let's try that. So here we see that z-score is -1, that's 0, and 1. And that makes sense. Your z-scores totaled together should roughly equal 0 because you're getting how many distance away on the positive side, how many distance away on the negative side, and they should balance out if you really have the mean. And so let's check this formula. Yep, it's using B3, but it has the average, and it's getting that standard deviation. Perfect. All right. So once I have that, I could actually just copy and paste this over here. And here we see, now it's using C and this average and getting the standard deviation of this data. Perfect. And we see roughly, you know, the negative side adds up to the positive side. Okay. So now that we have these individual z-scores, now we need to get the z-scores for fat multiplied by the z-score for cost. And that's real easy. This times this. For every single data point or case that we have. And we have 3 cases here, the 3 different brands of pizza. Right? Once we have that, instead of the average, well, actually we could just get the average all at once because we could just put it all in one formula, right? We could just sum these together. Could sum those together. And we want to divide by n-1. In this case, it's 2, right? If you wanted to put in a formula, you could put in count -1. But I'm just going to put, for our purposes, 2 here. Okay. And here we get a very, very high correlation where it's very, very close to 1. As cost goes up, z-score goes, as cost goes up, fat goes up, right? As cost goes down, fat goes down, right? And so they have a very positive correlation, and it's very liney. It adheres very closely to the line, right? And so here we could see that that this data is very, very highly correlated. It has a strong correlation. We don't have a lot of points, but apparently they fall very, very close to the line. All right. Okay, so previously we found that the regression line for this data is this. And I believe that in that case the cost is $17.50. $18 and $20. But previously in the regression lesson, we already found this. So check that the relationship between R, from the previous example, and B1 holds. Okay, so it's asking us, okay, is this really true that B1 in this example, and we're not going to do the formal proof, but just to see for ourselves, does B1 really equal the proportion R times the proportion of the variation from Y over the variation from X? Is this relationship really true? Well, we already know B1, right? So that's B1 right here. 0.125. And we already know R, right? We know R. This is something like 0.94, I think. And so we want to know, does 0.94 multiplied by S sub y over S sub x, does all of this equal 0.125? Well, let's see. That's not too hard. I'm going to move that up here. And so we have R right here. And so here, I'm just going to find S sub y and S sub x and multiply it by it. So I'll just create another column for standard deviation. And let's get the standard deviation for x and the standard deviation for y. And I want to know, is this R times the standard deviation of y over the standard deviation of x, is that going to be equal to 0.125? Moment of truth. Voila! What do you see? Yeah, so that relationship holds, right? So here we have, B1 and R. Move it over to this side so we know what these things are. And there you have it. We see that the relationship between R and B1 holds. Because there's sort of a little bit of rise for a lot of run, we know that this line is pretty shallow. And that makes sense. This is a pretty shallow slope. There's little rise over run, and because of that, it's a fraction less than 1. All right. So example 3, the mean score on a math achievement test for a community college was 504 with a standard deviation of 112. For the corresponding reading achievement test, the mean was 515 and the standard deviation was 116. The correlation coefficient is very high. Use this information to find the regression line. So here we see that we have the correlation coefficient, but they don't give us the data, right? So can we still do this? Yes, we can, because there is a relationship between the correlation coefficient and the standard deviations. There's a relationship between the correlation coefficient and slope, and all we need to know are the standard deviations in order to find this. So B1 equals R times S sub y over S sub x. And we actually know S sub y and S sub x and R, so we could find B1. Once we know B1 and we have the point of averages, right? So we have point of averages, which is x bar, y bar, right? And that is, we'll say this is x, and we'll say the reading is y. So here we have 504, 515. So we have, we could get the slope, and we could have 1 point of averages, and voila, we could find the intercept, right? So let's go ahead. R is going to be 0.7, and S sub y, which is the reading one, is 116, and S sub x is 112, which is the math score, right? So we could find B1, and I'm just going to use a little bit of space down here to just do the calculations. Feel free to do this on your calculator. So 0.7 times 116 over 112. And so that's 0.725. So I have here 0.725 as my slope, right? Once I have my slope, I could put that into my slope-intercept line formula. So my y is 515, and I'm looking for the intercept. Oops. And I add that to 0.75, 0.725 times my x, which is 504, right? So why don't I go ahead and just solve that in here? That's going to be 515 minus 0.725 times 504. Right? And I get 149.6. My B sub 0 equals 149.6. Right. So now that we have these two ideas, we can now find our regression line. So our regression line, in order to predict y, is going to be B sub 0, or the intercept, 149.6, plus 0.725 times x. And so that's our regression line. Here we see that the slope is less than 1, so it's less rise, more run, right? So it's a more shallow slope. And so, yeah, so you don't need to have all the points in order to find the regression line. All right, example number 4. Find the correlation coefficient for this set of data. And this set of data is provided for you on the download below. So if you go ahead and click on example 4, that data is all there. So previously we've looked at this data and we thought, oh, this is pretty good, pretty strong linear correlation. Let's see if our eyeballing was actually right. And I'm just going to move this one over a little bit because we're not going to need that as much. Let me shrink this down a little bit. So it always helps me for myself, just to think about, okay, I'm trying to find correlation coefficient. I know it's the average product of the z-scores, so I need to find the z-scores, right? So I need to find the z-scores for what I'm going to call the student-faculty ratio, SFR. And I also want to find the z-score for cost per unit, CPU, right? And so let's go ahead and do that. In order to do that, it's often helpful if you have the mean and standard deviation. So why don't we find the mean and standard deviation somewhere? So here, let me just get the means here. How about this? I'm just going to move this over by one column, just so that I could write mean and standard deviation. Because sometimes we'll get confused as to like what we were doing, and so it's often helpful to write these things down. And I like to put it in a different color because that helps me know, okay, wait, this is not part of my data. So let's get the average, the mean, of all of our data here. so the data for the student-faculty ratio, as well as the cost per unit. Now let's also take that same data and find the standard deviation, because we're often going to need that for z-score. So it's just useful to have it in advance. Great. So we have the mean and standard deviation. And here I'm just going to put a little divider here for now so that I can move this down. All right. So notice that it skips from row 7 to row 34. All right, now let's find the z-scores. Now that we have mean and standard deviation, it should be really easy, because it's just the difference between my point and my average, all divided by standard deviation. And I want to lock down that mean. Oops. I want to lock down that mean and average. And remember, as long as it's in the same column, it'll always use B. But I do want it to use E when I move over. So I'm not going to lock down the B part. I'm just locking down the row. And I get a z-score of negative 1.556, right? And so if my z-score calculations and my mean and all that stuff are correct, I should roughly have z-scores that are both positive and negative, and they should roughly balance out. So let's take a look at our data, and it seems like, yeah, roughly like half of them are negative and roughly half of them are positive. They should balance out. Once I have that, I could actually take all of these guys and drag that over. And let's check one of these formulas here. So this one, it gives me this point, the deviation or the difference between this point and the mean divided by its standard deviation. So perfect. All right. So once we have that, I know I need to multiply and get the product of these z-scores. So z of SFR times the z of CPU. Oops. So let's see what we can do here. Here, I'm just going to multiply this times this for every single one of my points. I'm just going to drag that all down. Great. And once I get down here, I know I need to find the mean of these points. So I'm going to find, but I don't want to use just the formula for mean, because that's going to divide by n. But I want to divide by n minus 1. So why don't I split it up into adding all of these up? So I'm going to sum them all up. Okay. So I'm going to sum them all up, and then I'm going to divide by count, instead of counting all of these. I'm just going to use the same points here. I'm going to say count all of these, and then subtract 1. And put that all in my sort of green parentheses. I think I have one extra set of parentheses there. All right. And we get a negative slope that's pretty high. It's, above 0.8. And so let's take a look at our data to see if that makes sense to us. Well, we certainly understand why it's negative. It makes sense that R is negative. And we did think it was pretty good. We did think it was pretty strong. And it does end up being pretty strong, 0.86 or 0.87. Great. All right, so that's correlation coefficient. See you next time on educator.com.